Alright, for this lecture we are going to discuss binomial coefficients. So we've already introduced binomial coefficients via their first interpretation, which is that the binomial coefficient n choose k is the number of subsets of the set of integers 1 through n that have exactly k elements. Now in this talk we're going to go over three other interpretations. The second interpretation pops up when you study bit strings, and a bit string is just a sequence of numbers, and the numbers have to be either 0 or 1. So this is a bit string of length 1, 2, 3, 4, 5, 6, 7, 8, 9, length 10, and it has 1, 2, 3, 4, 5 ones. And so now we will list all the bit strings on 4 symbols. And so here they are. When n equals 4, there are exactly 16 bit strings. You can verify for yourself that these are all 16 of them. And I grouped them by line based on how many ones there are. So we see that there's exactly one bit string of length 4 with no ones in it. On the other hand, we see that there are 4 bit strings of length 4 that have exactly 1, 1. And there are 6 bit strings of length 4 that have exactly 2 ones. And 4 bit strings of length 4 that have exactly 3 ones. And 1 bit string of length 4 that has exactly 4 ones. And so if you've ever seen Pascal's triangle before, you would actually recognize that you're seeing 1, 4, 6, 4, 1, which happens to be the binomial coefficients in order. So you do actually get the binomial coefficients, and on the next slide I'll explain why. So one way to study these types of problems is, given a bit string of length n, what we want to create is a subset of n, and in this case the value of n is 1, 2, 3, 4, 5, 6, 7, 8, 9. So a subset of the integers 1 through 9 of size 4, and the way the construction works is, to this bit string you associate these integers between 1 through 9, where the ith value in the bit string is 1. And so in this case, we highlight the ones. They occur in this particular example in positions 1, 2, 3, 4, 6, and 9. And so we're replacing a bit string with just the set of locations where the ones occur, and this is a subset of the same, the size of this subset is the number of ones that appear in the bit string, and it is a subset of the number of numbers in the bit string, the length of the bit string. And so this does actually get you from bit strings with k1s and length n to subsets, which was our first interpretation of the integers 1 through n of size k. And it turns out you can actually go backwards given a subset. For instance, let's say 1, 3, 7, 8. You could see exactly which bit string that had to have come from. Well, the first entry had to have been a 1, the second entry is a 0, the third entry is a 1, the fourth, fifth, and sixth entry are zeros, the seventh entry and the eighth entry are 1s, and the last entry is a 0. So this subset identifying where the 1s occur uniquely defines the string. And thus we do see that the number of bit strings with k1s of length n has to be equal to the number of subsets. So now we discuss the third interpretation of binomial coefficients in terms of lattice paths. And so the idea of a lattice path is if you're living in a city with a grid layout and you're riding around in a taxi cab and you're trying to get from one place to another, the only directions you can go is due north or due east, assuming of course you're going someplace to your northeast. And so you can only go down streets and up streets. You can't really drive through buildings, that's usually illegal in this country. And you can't jaywalk, so you can only do those types of steps. And so the idea is we want to count how many ways to get from point A to point B, only going north and only going east. So for instance, suppose we are considering all the ways you could get from the origin 0, 0 to the number 2, 2, going only north and east. And we see that there are exactly 6 different ways you can do it. You can either go all the way east, and then all the way north, or go all the way north and then all the way east, or you could do one of these paths that involves a lot more turns. Go east, then north, then east, then north, east, north, northeast, or so on. And so these are the only 6 ways you can do it. And it turns out that the number of lattice paths from 0, 0 to mn, where m and n are positive integers, is actually also a binomial coefficient. And one way to see that is to actually replace the directions with a binary string. And so the way the coding works is you replace an east step with a 0 and a north step with a 1. So for instance, if I take this last path, I saw that I go north, then east twice, and then north. And so I could record this. You could think of it as a Google Maps directions. Google Maps step by step has to tell you exactly which direction to drive. It is telling the reader exactly which direction to drive. And so you see, given a lattice path, by writing down the directions, you get a bit string. And we note that the bit string has length m plus n. And the reason why that is because if you can only go north and east only one step at a time, it's going to take you m plus n steps to get where you're going. There's no way around that. And so the directions have m plus n steps in them, so the bit string has length m plus n. But you had to do n east steps. N north steps. And so you have to have n ones. And therefore, to each lattice path, you have a bit string of length m plus n with exactly n ones, and that's exactly what we wanted. And vice versa, if you take such a bit string and drive using it as directions, you will actually get from 0, 0 to mn. And thus we see this is another interpretation of the binomial coefficients that actually pops up a lot with proving certain types of results, to view it as counting the different driving directions from point A to point B. And finally, the fourth interpretation of binomial coefficients comes from the binomial theorem. They are called binomial coefficients because they're the coefficients when you expand a power of a binomial in terms of the individual powers. That is, if you add 2 numbers, x and y, and you raise them to the nth power, it turns out you can rewrite this as a summation of powers of x times powers of y's, and this is exactly the formula. The binomial coefficients pops up right here. So for example, how one actually tries to prove this, although I won't do the full proof yet because we're not actually at a point in the course where we can do it. If I take x plus y and I cube it, well, what does it mean to cube something? It's to multiply it by itself 3 times. And to aid with reading, I'm using colors here, black, red, and blue. And so if you multiply a bunch of sums, you have to FOIL, and if you FOIL properly, either you have an x term first, times the rest, our y term first. And so after doing all the distributive properties and using no commutative properties, these are the 8 expressions you get, where each one has a black term from the first product, either a black x or a black y, a red term from the second product, either an x or y, and a blue term from the third product, either an x or a y. And so we see that there are 8 terms. And if you interpret x as north and y as east, then it looks like you're actually looking at bit strings or lattice paths. So strings involving exactly 2 characters, and all of them are appearing. All the different strings of length 3 involving x and y appear. And so you could try to group them together by the number of x's and the number of y's. So for instance, you can ask yourself, how many strings have only x's? And we see there's exactly 1. How many strings have exactly 2 x's and 1 y? Well, there's exactly 3 of them. That one, and that one. So these 3. And similarly, exactly 3 strings with 1 x and 2 y's, and exactly 1 string with only y's. And so we see the main reason the binomial theorem is true is because, in general, it turns out if you do the distributive properties of multiplication and FOIL properly, you're really looking at summing over all possible binary strings of length n, where you're replacing 0 with x and 1 with y, or vice versa. And then by the addition principle, a simpler way to compute this sum is to group like terms. And so the reason why the binomial theorem holds is because you're going to get exactly n choose k bit strings with exactly k ones and n minus k zeros, and we're interpreting ones as x and zeros as y, and so you actually do get the binomial coefficients as your expressions. And on the next slide, I will show you the Pascal's triangle written out just to end the talk. So here is Pascal's triangle, and so you read the top row as being the 0th row, and the leftmost entry is the 0th entry up to the nth entry. And so you actually do see Pascal's recurrence relation that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. What that says, and why it's called a triangle, is it says you can compute one of the values by adding the 2 numbers above it. And so you can keep this table going. So for instance, bring down some 1s. 8 plus 1 is 9. 8 plus 28 is 36, and so on and so forth. And so the binomial theorem tells you that if you wanted to, say, expand x plus y to the 5th power, what you would do is you'd start with this row, 0, first power, second power, third power, fourth power, and 5th power. Here you go. And that this row would tell you the coefficients of what happens when you expand x plus y to the 5th. As we've also seen, the binomial coefficients are also important because they count subsets and lattice paths, as well as bit strings.